Okay, this is problem number 8 from the AP Physics 1 Forces packet. And what we have here is we have a 3-block system. We have M1, M2, and M3. And M1 is being held to the wall here by this rope here. And it's sitting on top of M2, which is attached to M3 with this other rope. And so when we release the system from rest, M3 starts falling. M2 will slide to the right, and M1 doesn't go anywhere because it's locked into place by this rope. And we have two separate coefficients of friction. We have a mu1 here between the two blocks, M1 and M2, and we have mu2 between the M2 and the surface. And so part A asks us to draw a free body diagram, a force diagram for each object in the system, and so that's what we're going to do. We're going to start with M1. M1's the easiest one because it's not going anywhere. Actually, I guess the hanging block would be the easiest one. M1 has 4 forces on it. It's got its force of gravity, as always. And so we're just going to make that M1G. It's got a normal force, and this is coming from its contact with M2. It's sitting on a surface. In fact, it's sitting on M2 in this case. That is its surface. And so this will be our normal force. And it will be balanced because it's not going anywhere. And so if we need to come up with an equation for the normal force, we know it's going to be equivalent to gravity. And then it is 2 forces. There's the rope, which is holding it to the wall here. And we're going to call this tension 1 because there's 2 ropes in this problem. So this will be T1. And then the force that actually was going to drag it this way would be the force of friction. Because if the rope wasn't there, it would hitch a ride on M2 and travel right along with M2. And the reason it's doing that is because there's a force of friction between M1 and M2 that's letting that happen. And so we have a formula for friction that we can always apply. We know that the force of friction is going to be equal to the coefficient times the normal force. Actually, in this case, it's static friction. Well, no, in this case, it won't be static friction. It would be static friction if the rope wasn't there and M1 was sliding along with M2. But because M1 is locked in place and can't move, this will be kinetic friction. These two surfaces will actually be grinding along each other. And so we're going to use this formula, and we're going to take advantage of the fact that we know the coefficient of friction is mu1, and we know the normal force is equivalent to M1G, same as the gravity. And so the force of friction on this guy is going to be equal to mu1 times M1G. And that will be my force diagram. The reason I want to have these variables in here is because those are the variables that show up in my problem. And so when later on in the problem, when it asks me to do equations with just the variables in the problem, I can do that because I've got it just in the variables of the problem. In fact, we can solve B right now. It says solve for the tension in the cord that is attached to M1, so this T1 here, in terms of only the variables shown in the diagram and fundamental constants, which usually means we can use gravity. And there we go. We've already done this. We know that this block is not moving, and so these two horizontal forces have to cancel as well. And so tension 1 is going to be equal to mu1 times M1 G, which is pretty much, we're good to go with part B. We've got mu1, M1, and G are all allowed variables. mu1 and M1 show up in the diagram, and G is the constant that we're allowed to use. So we went ahead and answered part B. But let's go ahead and do force diagrams for the rest of the system. I'm going to do the hanging block next, since it's pretty easy. We're going to do M3 over there. It only has 2 forces on it. It's got its own force of gravity, which looks like M3G. And it's got this tension force, and this is the other rope in the problem. So we'll call this tension 2, 2 separate ropes. And that would be the force diagram for it. And if we wanted to use Newton's second law, which is always a good idea in these cases, we use Newton's second law here. It just so happened all the forces were balanced because the net force was 0. This thing wasn't moving. But in this case, the hanging blocks case, when we release this from rest, it will accelerate downward. So I know that the gravity has got to be the bigger force. I know it's going to accelerate downward. I'm going to go ahead and call downward my positive direction. because remember, you can call whichever one you want the positive direction as long as you're consistent. And I like to call the way I'm going the positive direction. And if you'd rather call this a negative direction, that's fine too. It just means you have to have a negative acceleration and make this force of gravity negative. But if I call the downward the positive direction, I'll end up with m3g minus T2 equals my net force, and that equals to the mass times the acceleration of block 3. And so I've got Newton's second law. This is F net equals ma. Remember, I'm doing net force two different ways. I can find it by subtracting my forces, and I can also find it through the formula, Newton's second law, F net equals ma. And so that would be for the hanging block. For M2, it's a little more complicated. We have more forces on it. So I'm going to do M2 right here. It looks like we're going to have some horizontal forces. And so M2, if we look at it, it of course has its force of gravity. So that's M2 times g. And it's sitting on a surface as well. And so it has a normal force. And those would be balanced. And you would look at the picture up here and you would see that this rope here, tension 2, the same rope that's attached to M3 is pulling it to the right. So I'm going to go ahead and put my tension 2 right here. And it's got two forces pulling it to the left. In this case, it's got friction between it and the ground, but it also has friction between it and M1. It's got both of its surfaces grinding against the motion. And so we have two forces of friction in this case. We have a force of friction from M1 and from the ground. And we already know the force of friction from M1. Force of friction is equal to mu1 times M1g. That was the same force of friction from the ground. I'm sorry, from M1 up here. This is the same force of friction that M1 experienced. It's just equal and opposite. This is a Newton's third law pair. So it's got this force of friction, which is equal to mu1 times M1g. That'd be the first force of friction, same one that the top block felt, M1. And then I would have the force of friction between it and the ground. And its force of friction would also be mu times the normal force. In this case, it would be mu2 and its own normal force. But we got to be careful because M1 is sitting on top of it. And if M1 and M2 are sitting on top of each other, then we're going to get that additional push downward from M1. And so the gravity in this case is going to be, I guess we'd add that to the force diagram, right? Isn't the force of M1g also pushing down on M2? It is. It's on top of it. We can't forget that. We got that additional gravity hanging on there, and so our normal force will actually, in this case, be equal to M1 plus M2 times g. Both of these forces of gravity must be balanced by this normal force. So it's important not to forget that. And so that makes our force of friction here, the second force of friction, it's going to be, screw that up. It's going to be mu2 times, let's see if we can get this in with two parentheses here, M1 plus M2 times G. I guess I got to close my other parenthesis. Looks a little ugly, but I got both mg's times mu. I got the normal force times mu2. And so that would be the force diagram for that. And so we've satisfied A. These two forces balance with this, and my net force would come from these horizontal forces. If I were to do Newton's second law for this one, it would be tension 2 minus force of friction 1 minus force of friction 2. That would be the net force. And if I slid in all the variables I have, it looks like tension 2 is going to be minus mu1 times m1g minus mu2 times m1 plus m2g. I'll just write it like that. And that's going to be equal to mass times acceleration for block 2. So it's going to be equal to mass 2 times acceleration. That would be the net force expression for block 2. And so if I want to go ahead and solve for the acceleration of m3, then I have to, which is part B. Remember, we've done part A. We've got a force diagram for each one of them. I've gone ahead and used Newton's second law for each one of them. So this will be Newton's second law for this one. And then what I want to do now is I want to solve for acceleration of m3. And so I look up at m3, and I've got my m3g minus t2 equals m3a. So I can have all the variables in there except for t2. I got to get rid of t2. And fortunately for us, we have an equation that gets rid of t2. It just so happens to be this really long one down here. And so what I'm going to do, let's slide this up a little bit. Hopefully you have the problem still in front of you. Is I'm going to rearrange this for t2, and I'm going to substitute it in here for t2. And that way I can get rid of t2 in my problem. We do this a lot in physics. We take one equation and sub it into the other. And so if I rearrange this, basically I'm just going to move these two terms to the other side. I get t2 is equal to m2a, and these are both negative terms, so I would add them to the other side, plus mu m1g plus mu2 m1 plus m2 g, and it will look like that. And now I can take this giant thing, which is all equivalent to t2, and I can sub it in up here for t2. And so ultimately I'm going to end up with this. I'm going to end up with m3g minus, and then this whole thing right here, which is all equivalent to t2. So I got m2a plus mu, oh, I forgot the mu1 up there, mu1 m1g plus mu2 m1 plus m2. You just got to be very careful when you're doing this not to make a mistake. Go slowly and methodically through there. Make sure you don't screw anything up. So this is all t2, and that's equal to m3a. So I substituted this whole giant thing, which is equal to t2, up here for t2. And now what I'm going to do is I'm going to distribute the negative sign. So I'm going to end up with this. Make sure the negative sign goes to each term. So that becomes negative. This one becomes negative. This one becomes negative. Remember, this is still one term, right? This m1 plus m2 is in parentheses. It's all combined into one term. Equals m3a. And now all I'm going to do is I'm going to get that m2a to the other side, get it out of there, so I can combine like terms. And so I'm going to take my m3g minus mu1, m1g minus mu2, and I know this is long and tedious, but you got to make sure that you go methodically through this and not make a mistake, and you end up with m3 plus a plus m2a. See, I almost made a mistake. And what you can do now is from this part here, you can factor out the a. This turns into, let's go ahead and slide this up a little bit, this turns into a times m2 plus m3. Basically, I took the a out of each one and I moved it to the outside. And so what happens is now I can take this m2 plus m3 and I can just divide it to this other side. And so I can take this whole long equation right here and divide it by m2 plus m3, because I'm just treating this as a single term and I'm dividing it out, and leave a all by itself, which is the point. That's what I was trying to get. So a ends up equaling this right here, this giant term here, which seems like a lot, and I guess it was a lot, but as long as you systematically work your way through it, it's not too bad. You just got to be careful to go very carefully, make a mistake, and they won't make a mistake when you're doing this. And so try not to rush, but you're still just applying Newton's second law. You're still just making force diagrams and working with net force. At the end of the day, that's all you're doing. You're just working with symbols instead of variables. I mean, symbols instead of numbers. My fault.